Today we are going to discuss a few applications of Laplace transforms. Mainly, we are using Laplace transforms to solve differential equations, and we are using the result, which gives the Laplace transform of derivative of a function. We have the result like Laplace transform of f dash t is equal to s into Laplace transform of f of t minus f of 0, and Laplace transform of f2 dash t is equal to s square into Laplace transform of f of t minus s into f of 0 minus f dash 0, and the Laplace transform of f3 dash t, that's equal to s cube into Laplace transform of f of t minus s square into f of 0 minus s into f dash 0 minus f2 dash 0. So we can use this particular result to find the Laplace transform of derivative, or to find the Laplace transform of f of t if the Laplace transform of f of t is unknown but the Laplace transform of f dash t is known, and the value of the function at 0 and its derivatives at 0 are known. So that is how we used this particular expressions in our previous sessions. Anyway, the same set of equations can be used to solve uh, linear differential equations with initial conditions. So what we are going to do is illustrate how we can solve a linear differential equation with initial conditions, that is the value of f at 0, f dash at 0, f2 dash at 0, they are given. If they are given, then we can solve the system of linear differential equations using Laplace transforms. Anyway, this equations or this result can be extended to nth derivative, but in practical sense, in our say in our situation, we are not going above third derivative, third order differential equation, or at most fifth order differential equations. So anyway, let's illustrate the concept using the help of a simple differential equation. So let us start with a simple differential equation. Let's say Laplace find the solution of y2 dash plus 5y dash plus 6y is equal to e raised to minus 2 into t. That's a differential equation, and it is given together with an initial condition y of 0 and y dash 0 are equal to 1. So this is our initial conditions. So it's actually an initial value problem, and this is our differential equation. So the process is okay. By the term solution, what we mean is a relationship between y and x, the dependent variable and independent variable. Here the independent variable is t. So a relation between y and t, something of the form, say f of y t is equal to 0, or y is equal to f of t. This kind of a relation is what we are looking for, and while solving a second order linear differential equation, the solution will have solution will contain some arbitrary constants, c1 and c2, and we eliminate these c1 and c2 using the initial conditions. Since we have two unknowns, we need two initial conditions to find the exact values of our the arbitrary constants. So that's the analytical method which we are familiar with. So first we solve the given differential equation using we write down the auxiliary equation and solve it, and write down the complementary function. Then we find a particular integral. Complementary function plus particular integral will give the required solution, and that solution will contain two arbitrary constants, and that two arbitrary constants are eliminated by using the initial conditions. That's the procedure which we are familiar with. And now we are going to illustrate a method in which we use the concept of Laplace transforms to solve such problems. So for that, if it is our equation number 1, then we take taking Laplace transforms of the equation number 1. What happens? The Laplace transform of y2 dash plus 5y dash plus 6y is equal to the Laplace transform of e raised to minus 2t. And we just calculate or just write down the Laplace transform of y2 dash. Okay, anyway, the Laplace transform is a linear operator, so it becomes Laplace transform of y2 dash plus 5 times Laplace transform of y dash plus 6 times Laplace transform of y is equal to the Laplace transform of e raised minus 2 into t. Now the Laplace transform of y2 dash. The Laplace transform of y2 dash is s square into Laplace transform of y minus s into the value of y at 0, that is f of 0, minus y dash 0, then plus 5 times Laplace transform of y dash, Laplace transform of first derivative, which is given by s into Laplace transform of y minus y at 0, then plus 6 into Laplace transform of y is equal to the Laplace transform of e raised to minus 2t. Laplace transform of e raised to minus 2 into t. Now we substitute the known values. So anyway, we don't know what's the Laplace transform of y, so we keep it as it is. So L square into Laplace transform of y minus, for simplicity, we can write Laplace transform of y as capital Y. That's all. It's okay. Okay. Anyways, it is s into y at 0, that is 1, minus y dash at 0 is also 1, plus 5 into s into Laplace transform of y is an unknown, then minus 1 plus 6 into Laplace transform of y is equal to the Laplace transform of e raised to minus 2t is known. E raised to at, it is 1 by s minus a, so it is 1 by s minus minus 2, that is 1 by s plus 2. So now we just rearrange the terms on the left hand side. The Laplace transform of y is taken as a common factor, and the coefficients are s square Here, here we get a 5 into s into Laplace transform of y, so it is plus 5s. Then the remaining term here, it is 6 into Laplace transform of y, so it is plus 6. So they are the terms, coefficients of L of y. Then the remaining terms, here we have a minus s, here we get a minus 1, and 5 into minus 1 is minus 5, and that's equal to 1 by s plus 2. And just we rearrange it, we get L of y into s square plus 5s plus 6 is equal to 1 by s plus 2, 1 by s plus 2, uh, 1 by s plus 2 minus, what is obtained here, this minus s minus 1 minus 5, so it is minus s minus 6, so it is minus of s plus 6. So that is equal to, we can take s plus 2 as the LCM, and what we get is uh, s plus 2 out of 1, then s minus s plus 6 into s plus 2. Now what we are looking for is Laplace transform of y. Laplace transform of y is equal to, here we can expand the numerator, this 1 minus s into s square, uh, then 6x plus 2s, that is plus 8s, then 6 into 2, that is plus 12, and the denominator we have s square plus 5s plus 6. Now what we are looking for is a solution to the given differential equation that can be obtained by calculating the value of y. So what we are looking for is y equal to L inverse of this particular expression, and for that we can simplify it as um, so we can simplify it as L inverse of, so one thing here, what we have is minus s minus 6. If we transform it to the to here, it becomes plus, and this is a positive sign. Okay. Now what we are looking for is the y is equal to the inverse Laplace transform of, if we simplify it, what we have is s square plus 8s plus 12 plus 1, that is 13, divided by s square plus 5s plus 6. And when we calculate the inverse Laplace transform of this thing, um, we get the required solution of our term. So here we have an s plus 2 also, don't circular mistake. So also we have an s plus 2. Now how we have to find the inverse Laplace transform. So this is equal to L inverse of s square plus 8s plus 13 all divided by s plus 5s plus 6, that is s plus 3 into s plus 2 into s plus 2. Now we have to use Marketa's equation number 1, that's the value of y. Take it as equation number 1. Now we are going to use partial fractions to write the function s square plus 8s plus 13 divided by s plus 3 into s plus 2 into s plus 2, that is s plus 2 the square, as something like a divided by s plus 3 plus b divided by s plus 2 plus c divided by s plus 2 the whole square. And we have to find the values of a, b and c. That gives s square plus 8s plus 13 is equal to a into we take s plus 2 the whole square into s plus 3 as the LCM, so it is a into s plus 2 the whole square plus b into s plus 3 into s plus 2 plus c into uh, s plus 3. Now from here we need to find the values of a, b and c. Okay, so to find the value of okay, if we substitute s is equal to minus 2, this time will vanish, the second time will vanish, and what remains is the third time, and we have s is equal to minus 2 will give uh, minus 2 square, that is 4, plus 8 into minus 2, that is minus 16, plus 13 equal to when s is equal to minus 2 plus 2 becomes 0, 0 square is 0, so this time will first time is 0, second time is also 0, and the third time is c into minus 2 plus 3, that is 1, so implies c equal to minus 16 plus 13 plus 4, 13 plus 4 17, 17 minus 16, that is 1, so c is equal to 1. Now we can find the value of a by substituting s is equal to minus 3. When s is equal to minus 3, this particular term will vanish. The second term will also vanish, and what remains is the term of a. So it is s square, that is 9, then 8 into minus 3 minus 24 plus 13 is equal to a into minus 3 plus 2. Minus 3 plus 2 is minus 1. Minus 1 the square is 1. So that gives a equal to minus 24, 13 plus 9. 13 plus 9 is 22. Um, 13 plus 9 is 22, and so a is equal to minus 2. So that's the value of a. A and c is given. Now we have to find the value of b. So for that, I think it's better to compare the coefficients of s square on both sides. So here, by comparing coefficients of s square on both sides, um, what we get is here left hand side the coefficient of s square is 1, and right hand side from the first term it is s plus 2 the whole square, so s square plus 2as plus 2 square, so there is a term of s square and the coefficient is a, and here it is s into s into b, so that's the coefficient is b. A plus b is equal to 1, and that gives b is equal to 1 minus a is equal to 1 minus minus 2, that is 1 minus minus 2, that is 1 plus 2 is equal to 3. So we find the values of a, b and c, and we substitute that values in this particular expression, and we get a by s plus 3 plus b by s plus 2 into c by s plus 3 equal to uh, a is minus 2 by s plus uh, 3 plus b equal to, what's the value of b is equal to 3 by s plus 2 plus c equal to 1, so 1 by s plus 2 the whole square. That's the uh, expression we obtained by taking Laplace, the using the partial fractions. Now, calculating the L inverse of this expression, we have this equal to L inverse of minus 2 by s plus 3 plus L inverse of 3 by s plus 2 and plus L inverse of 1 by s plus 2 the square, and this is equal to, by calculating the inverse Laplace transform, minus 2 is a constant, and the inverse Laplace transform of 1 by s plus 3 is e raised minus 3t plus, here 3 is a constant, the inverse Laplace transform of 1 by s plus 2 is e raised to minus 2 into t plus, here 1 by s plus 2 the whole square is the inverse Laplace transform of, here it is something like 1 by s square. 1 by s square is the Laplace transform of t, and when we use the shifting theorem, e raised minus 2t into t will give the Laplace transform 1 by s minus minus 2 the whole square. So using this the Laplace transform here, the inverse Laplace transform of 1 by s plus 2 the whole square is e raised minus 2 into t into t. So this is the inverse Laplace transform, and in equation number 1, this is the required value of y, or y of t. So this is the required solution of the given differential equation, and observe the fact that this particular solution, which can be sometimes can be written as y of t is equal to e raised minus 2t into uh, 3 plus t minus 2 e raised minus 3t. Okay, let it be that. So this particular solution contains no arbitrary constants. So when we use the usual method, we get a solution which contains a number of arbitrary constants, and we eliminate that arbitrary constants using the initial value or initial conditions. But when we use the method of Laplace transforms, we get the required solution uh, in a single step. We don't need to eliminate any arbitrary constants. The final solution is a particular solution which we need. So this method is very much useful when we have to solve a number of initial value problems, and that is why the concept of Laplace transforms has many applications in engineering. Okay, let us illustrate the same concept using the help of some more problems. So let's another problem. Consider the differential equation y3 dash minus 3y2 dash plus 3y dash minus y is equal to t square into e raised t. So uh, differential equation in which have a third order derivative. Anyway, by just calculating the Laplace transforms on both sides, we have Laplace transform of y3 dash minus 3 into the Laplace transform of y2 dash plus 3 into the Laplace transform of y dash minus the Laplace transform of y is equal to the Laplace transform of t e raised t or minus t plus t. Okay, plus t. That is, it is equal to s cube into Laplace transform of y minus s square into y at 0. Okay, then we should provided with s number of initial conditions, and the initial condition, let me check, it is y at 0 equal to 1, y dash is at 0 is 0, and y2 dash, since the y2 dash at 0 equal to minus 2. These are the initial conditions. Initial conditions. Okay, so it is s cube into L of y minus s square into y of 0 minus s into y dash 0 minus y2 dash 0, then minus 3 into s square into Laplace transform of y minus s into y at 0 minus y dash 0, then plus 3 into uh, Laplace transform of y dash is s into Laplace transform of y minus y at 0, then minus Laplace transform of y equal to the Laplace transform of t e raised to t. Laplace transform of t e raised to t. Now we can make some simplifications. First thing, we write down the coefficients of Laplace transform of y together. So it is s cube, here s cube, and here we have a minus 3 s square, and here it is plus 3s, and here it's a constant term, so it is minus 1. And now this into here we substitute the values of y of 0, y dash 0 and y dash 0. We know that y of 0 is equal to 1, so the remaining terms here is minus s square. Y dash 0 is 0, so the second term will vanish, and the third term y2 dash 0 is minus 2, so it is minus of minus 2, that is plus 2, and here this term is already taken as the coefficient of L of y, and here minus 3 into minus s, that is plus 3s into y at 0, that is 1, so it is plus 3s, and y dash 0 is 0. Now plus here 3 into minus y of 0. Y of 0 is 1, so it is plus 3 into minus 1, that is minus 3, is minus 3, and this term is already taken. So this is equal to Laplace transform of t e raised to t. The Laplace transform of t is 1 by s, and by shifting theorem, t e raised to t has the Laplace transform 1 by s minus 1. So it is 1 by s minus 1. This t square, not t. So it is t square. So t square. So Laplace transform of t square is, so we need t square is 2 factorial divided by s raised to 2 plus 1, that is s cube. So the thing here is 2 by s minus 1 the whole cube. So this 2 by s minus 1 the whole cube. So that is the Laplace transform. Now this will give the Laplace transform of y into the term is s cube minus 3s square plus 3s minus 1, and the remaining term is moved to the right hand side, so it is s minus 1 the whole cube, then plus s square plus 3s, then plus 2 minus 3, that is minus 1. Now from this expression we have Laplace transform of y equal to 1 by, this is s minus 1 uh, the whole cube, so this s minus 1 the whole cube into, so this s cube minus 3 into x square into 1 plus 3 into s into 1 minus 1 cube, then 1 by s minus 1 the whole cube into, here it is 2 by s minus 1 the whole cube plus s square plus 3s minus 1. Now this is equal to, we can split the right hand side into 2. What we get is L of y equal to, the first term is 2 by s minus 1 L of y equal to 2 by s minus 1 the all raised to 6, and the second term is plus s square plus 3s minus 1. It's not an easily factorizable term, anyway divided by s minus 1 the cube. So there's a tricky method by which we can simplify the second time. So the first time keep it as it is, 2 by s minus 1 the all raised to 6, the inverse Laplace transform of which can be evaluated simply using the what we call the shifting theorem. Now the second time here is this plus s square plus 3s, so it is minus 3s, not plus 3s. This term is minus, and this is plus, so this is plus, and this term is minus. So clerical mistakes, and that is the main problem in such. Okay, so it is minus 3s. Okay, now how we will simplify this particular second term. So it is here plus. Now we express the numerator of this rational expression in terms of s minus 1. So what the process, it is we write like this, uh, s minus 1. So we have s square minus 3s plus 1. So first we need a term of s square. So in terms of s minus 1, this s minus 1 square. So we have an s square, but there is a number of extra terms. So that extra terms are subtracted. So it is s square plus 1 square plus 1 square is subtracted, and there's a 2ab term, 2 into s into 1. So minus 2ab is again subtracted. So it is 2 s, then minus 3 plus 1, and that's equal to s minus 1 the square. Then the remaining terms uh, written as plus 2s, uh, then minus 3s. Okay, yeah, yes. Here plus 2s, then there is a minus 3s, plus 2s minus 3s is minus s, so it is minus s, then minus 1 plus 1 become equal to 0. So this is how we can rewrite it, and that's equal to s minus 1 the whole square minus uh, of so we can write here's a minus s, so we can write it as minus s minus 1 minus s minus 1. So we have plus 1 additional, and that plus 1 is subtracted. So this is a process, and we do all this simplification only to rewrite the expression um, in such a way that we get a number of terms for which the inverse Laplace transforms are known. So it is s minus 1 the whole square minus uh, s minus 1 minus 1 divided by s minus 1 the whole cube, and this will give L of y equal to 2 by s minus 1 the whole raised to 6 plus we split it into three fractions. S minus 1 the whole square divided by s minus 1 the whole cube is 1 by s minus 1, then minus s minus 1 divided by s minus 1 the whole square, that is 1 by s minus 1 the square, and the last term being minus 1 by s minus 1 the whole cube. Now here altogether we have a shifting of erased t, so that erased t, uh, okay, if we take the L inverse, we get the solution y is equal to 2 into L inverse of 1 by s minus 1 the whole raised to 6 uh, plus L inverse of 1 by s minus 1 plus minus L inverse of 1 by s minus 1 the square uh, minus 1 L inverse of 1 by s minus 1 the whole raised to 3. Now just evaluate the inverse Laplace transforms, and here the inverse Laplace transform is, that is y is 2 into uh, The Laplace transform of t raised to 5 is 5 factorial divided by s raised to 6, or the inverse Laplace transform of 1 by s raised to 6 is t raised to 5 divided by 5 factorial. So, and here we have a shifting of uh, 1. So it is e raised t into e raised t into t raised 5 divided by 5 factorial. Then in a similar way, the second case, it is e raised t into 1 by s is the Laplace transform of 1 by s is the Laplace transform of 1. So it is e raised t. Then minus, okay, let me solve the equation in our frame. Okay, now it is plus, then minus e raised t into 1 by s square is the Laplace transform of t, then minus e raised t into 1 by s cube is the Laplace transform of t raised 2 divided by 2 factorial. And we can take this e raised to t as a common factor. E raised to t is taken as a common factor, and that will give the value of y as e raised t into uh, 2 t raised to 5 divided by 5 factorial plus 1 minus t minus t square by 2. So that's the required solution of the given differential equation. Anyway, here the tricky step is here. This is how we rewrite the term s square minus 3s plus 1 divided by s minus 1 the whole cube into a form for which the Laplace transforms are known. So that is how we use the concept of Laplace transforms to uh, solve differential equations. So that's how we use the concept of Laplace transforms to solve system of linear differential equations with initial conditions. So I recommend you to go through a number of problems to familiarize with this particular method, and this will be very much useful in your while solving your engineering problems, which include initial value problems. Anyway, by this, we're winding up the discussions on applications of Laplace transforms, and altogether the discussion of Laplace transforms. Now, um I recommend you to uh, go through a number of problems, because the main skill which you are required to acquire is nothing but the process or the skill to find the Laplace transform and the inverse Laplace transform of functions. That's the major skill which you are uh, required, or which you are um, able to, or you are the, what we call it as the outcome of this particular module. Uh, what we are looking for is the skill to find out the Laplace transform of a given function and the inverse Laplace transform of any given function. If you know how to find the Laplace transform and the inverse Laplace transform, then the solution of differential equation using Laplace transform is very simple. Okay, anyway, just go through a number of problems and be very much confident with the concept of Laplace transforms. And thank you.